Okay, so last time we developed a force balance for a material element that was a fluid in which there were no viscous stresses present, so we called that an inviscid material. And we developed this equation that we called the Euler Equation, which is nothing but a statement of Newton's second law on a per volume basis. It says mass per unit volume times acceleration of a material element is given by gradients in pressure, which come from from surface forces, and then also body forces. We're going to use this equation a lot as we go through this class, but the simplest applications we can make are actually if we think about this in the case where we're dealing with a system at rest or at equilibrium. So in hydrostatics, we're particularly interested in the case where the velocity is zero everywhere. And this equation, of course, simplifies dramatically in that case to be essentially a statement that says that the gradient of the pressure is equal to rho times g. And so we have to be very careful about pressures and densities here. So this is a pressure, and this is the gravitational body force. And essentially what that says in words is that if I take a little material element in a fluid like this, or if I think about a material like that, then in general what I'll find is that I have to support, at equilibrium, I have to support the weight of all of the material above me. And so the weight of the material above me says that I need a gradient of pressure to push back on that. And so the gradient of pressure is going to balance against that. And so the force acting on this coming from all of the weight above that means that there needs to be a high pressure at the bottom. So we should expect the pressure to be high here and decreasing as we move towards the top. And at the top, we expect the pressure to be atmospheric. And probably everyone who's ever been in a swimming pool will be very familiar with this, that the deeper you go, the higher the pressure gets, and the coefficient depends on the density of the fluid. There's one really important piece of sign convention that we have to be careful here that's just worth making sure that we write down, though, is that typically when we think about things like this, as I've mentioned, we normally think about gravity as acting downwards. So with a minus sign here, so gravity is acting in the negative z direction, and this can lead to confusion when if you're not careful. And so just to think about it, if we think about applying this in the z direction, then this equation in the z direction will say that dp by dz is equal to rho times the component of this, which will be minus g in the z direction. So there's obviously no component of gravity in the x direction, and so that says that the pressure at every single point across the bottom here is the same. Okay? If there wasn't a constant pressure, then there would be a gradient in the pressure, and that would lead to a flow until we find the place where this equilibrium is true. And so when we integrate this, we'll have to, if we want to integrate this to find the pressure field, we have to be very careful about where we integrate from. And so if we use a coordinate system, which I'll call z with a tilde over it or a twiddle over it, then when we integrate this, then our boundary condition, so if we were to integrate this in the z coordinate system, then we'll find that the pressure is equal to minus rho g z. As we expect, it goes down with increasing height plus a constant. And in this coordinate system, we would apply that the pressure at z is equal to the height of the material, and then we'll find that will be equal to a value that we'll call atmospheric pressure. And we normally indicate our datum, as people call it, where we're going to reference pressure by a little triangle like this. And the pressure there is PA. So at the end of the day, our expression becomes P is equal to PA plus rho G times H minus Z. So indeed, if I put in that Z is equal to 0, then I get that the pressure is maximum. If I put in that Z tilde is equal to H, then I find that the pressure is atmospheric. Now, alternatively, other people might do this the other way around. They might reference it from a coordinate system that's pointing in this direction. in which case we might call this direction z. And now in this direction, if we're doing this in this coordinate system, now our gravitational vector is equal to g times ez. And so we would end up with an expression that said dp by dz is equal to plus rho g. And our boundary condition, of course, would be that the pressure at z is equal to 0 is equal to PA. And so the same expression when we integrate this will be that the pressure gets bigger with distance into the fluid, and we would write indeed again that P is equal to PA plus rho G times Z. So those two statements are identical to each other, and we can see that all it really means is that there's a coordinate change from Z to h minus z. And so a good statement to recognize is that z is equivalent to h minus z hat when we do this. This may seem trivial, but it frequently causes lots of confusion when we're actually thinking about distributions of pressure fields. So where this is particularly useful in hydrostatics is by thinking about a distribution of forces on a wall. And so we might be interested in a wall of some length. And we might be asked to find, for example, there might be a door in the wall or a window in the wall with a location Z1 and a location Z2 at some depth below a free surface. And we might be interested in finding the effective force that's acting on this. So we might be interested in asking what is the force acting on this. And we're also going to have to think about where that force acts through. And so we'll call this force Fp, for the force coming from pressure, and we'll call the distance at which it acts Zp. People will often call this point the center of pressure. And so we can do that using this equation and just recognizing that we know that the pressure varies across here. And so we're just going to have to express this in terms of an integral. So if we're interested in an expression for Fp, we might write that Fp is equal to the sum of all of the little elements of force acting on a little piece of material of size dz. And we have an expression for that, and I'll choose to work in a coordinate system that's directed downwards, as we've done here. So we'll write this as an integral of this expression that we've got here, PA plus rho GZ, integrated from Z1 to Z2. And we'll have to integrate this over Z. Now, if we work out the units of this, we recognize that this is really a force per unit depth, because I haven't said anything about the depth of what's going in the into the board. So if we were to say the width of the wall is L into the board, then we need an L over there. Now we have a pressure times an area. And so we can also express this as, if people prefer. Sometimes people like to write it in terms of a force per unit length, and we could write that as Fp over L. So you'll sometimes see people use a prime to indicate per unit length. So we have an expression here, and we can substitute this and integrate this. And so at the end of the day, we'll find that our expression for the force looks like a length times Pa times Z2 minus Z1 from the first term. And then I have to integrate z, so I get a half rho g squared, and so we'll get rho g times over 2 times z2 squared minus z1 squared as an expression for our force. So this looks like the force acting on the wall also depends on atmospheric pressure. And then we'll just have to say something about what's happening on the other side of the wall here. And so typically, if we're dealing with, let's say, air on the other side of this wall, so if we have atmospheric pressure here and here. Then in reality there is also air acting on this side of the wall that's providing a pressure that's pushing back on the other side. So this term in fact cancels out on both sides. And so if we were to asking what is balancing on here, there's really a term that's coming from the pressure here. It would PA times Z2 minus Z1. And so these terms will cancel out, and so the net force above and beyond atmospheric pressure comes from just this contribution. So we might write that Fp over L is equal to 1/2 rho g Z2 squared minus Z1 squared. The final thing we might like to ask is where is the center of pressure acting through? And to find that, then we want to think about that we can either think about this as a distribution of forces, or we can think about it as a net force. And we can have a very nice geometric interpretation of this, that we can see that the pressure is increasing from the surface downwards. So as I move down like this, the pressure is actually increasing like this as we move down. And so it's largest at the bottom, and it's got some value that's given here. And what we're really doing is finding the integration of the area of this, and then finding the place at which it acts through. So we can take moments about this. So to find the center of pressure, which we'll just call COP, all we have to do is take moments and say that this system is equivalent to this system. So we might write that Fp times Zp is equal to taking moments of, again, multiplying it by the width of the system of the pressure, which is rho times g times z, multiplied by the moment arm, z, and the size of the element, dz. And so I have to integrate z squared. When I get that, of course, I'm going to get 1/3 and z cubed. We have to integrate it from z1 to z2. So this becomes Fp is L times 1/3 rho g z2 cubed minus z1 cubed. So now we have an expression for that. And if I combine these two, if I find a combination of these two, then I can now just substitute in here for our expression for where the pressure is acting. And so if I substitute for Fp in here, the L's are going to cancel. And the final expression we'll get is that the expression for the center of pressure is given by Zp. I'll divide through by this. The L's will cancel, and so I end up getting an expression that looks like 2/3. The rho g cancels, and it looks like z2 cubed minus z1 cubed divided by z2 squared minus z1 squared. And so we can easily find both the magnitude of the force and where it acts through. A very good thing to do is to think about the simplest case, which is when z1 goes to 0. If I go up to this point here, then this term goes away, and then we'll see that this looks very much like a result that I'm sure you've seen before, which is that this looks like it's acting through the centroid of our triangle. And this triangle is a triangle that tells you about the magnitude of the pressure that's acting on it, and also the position at which the center of pressure is, which for our triangle is at 2/3 of the height of it, which is given by Z2. So if we let this go away, things simplify. And for that reason, this is often called the pressure prism. And it's a very useful way graphically, if you're graphically minded, of understanding the idea of distributions of forces and where the force acts through, which is through the centroid of this prism.